We have been talking about iPhone. Let's look at the evolution of iPhone. Journey started off with A4. Then it has gone through various versions. And today we are talking about A17. A4 was based on 45 nanometer technology. The frequency was 1 gigahertz. A17 is based on 3 nanometer technology. And the frequency is 3.78 gigahertz. You see the difference. 1 gigahertz versus 3.78. And also you think about the complexity. A17 has more than 19 billion transistors. It's mainly because of the technology 3 nanometer. Technology is nothing but the size of channel. In CMOS, we find source, drain, and there is a channel in between source and drain. So in VLSI, what we do? We try to reduce the channel size. So here, 3 nanometer is nothing but the size of the channel. So what it reflects? This journey reflects Moore's law. The number of transistors in a chip doubles every 2 years. All right? So VLSI is a field which involves packing more and more transistors into smaller and smaller chips. Billions of transistors per IC. A17, it's pretty complex. It demands more than 19 billion transistors. So it's possible only because of progress in fabrication. It has been so good and efficient. There's a good progress in fabrication. Foundries like TSMC, they provide support for higher technology nodes like 3 nanometer. So what we do in VLSI, very large scale integration, we convert the existing PCBs into smaller and smaller chips using SoC design technology. All right. We have been discussing so much about SoC design, but how we implement the chip. We have two main options. One is ASIC, application specific integrated circuit, and the other option is FPGA, field programmable gator. Field programmable gators. We can buy the chip directly from companies like Xilinx, Altera, Microchip. Now Xilinx is part of AMD, Altera is part of Intel. We can buy the chip directly from the vendor. And what you can do is you can configure the chip with your design. You can download your design into the chip. When it comes to dealing with applications like routers, network switches, or printers, we can go with the FPGA. Also, FPGA is used extensively in the area like AI. AI accelerators can be realized using FPGA. FPGA is used extensively in space. Organizations like ISRO, they might prefer FPGAs because they have special hardware architecture which can support extensive mathematical applications. ASIC, application-specific integrated circuit. We prefer ASIC to customize area and power. So whatever the chips that we get from chip makers like Intel, AMD, Infineon, Samsung, Qualcomm, mostly they are of ASIC type. It's used extensively in products like smartphones, tablets, laptop, all the SoCs. We have seen M-series SoCs. We have seen Apple's chip A4 to A17. Everything is ASIC, application-specific integrated circuit. But the chip can be complex. The chip can be simple. It doesn't have to be like multi-billion complexity. It can be even a simple chip which might demand 1000K gates or million gates. For example, if I want to have IoT chip on my Blazer, I expect the chip to measure my body temperature, heartbeat, and I want the chip to communicate everything to my smartphone. And there could be some app. So in that case, area and power customization is very critical. How are we going to customize the parameters, area and power? That's where we need to work with foundry. So we make sure that the chip is very small. That might not be possible with the FPGA. They might be available in standard size. You can't customize area and power as you prefer. There could be some constraints. At the same time, you want to produce chips in bulk, like billions of chips. ASIC is the good option, right? So you need to work with external foundries like TSMC. Some of the chip makers like Intel, Samsung, they may have their own foundries. Some of the chip makers like AMD, NVIDIA, Qualcomm, they might be working with external foundries like TSMC, UMC, or Global Foundry. That's the main difference between ASIC and FPGA. We call this as ASIC because it is application specific. For example, you can't think of using M-series chips for some other application like smartphone. It's meant for desktop. The chip we create for a particular product, let's say tablet chips, it can't be used for smartphones. It can't be used for smartwatches. So it's application specific. Also, it's very expensive. ASIC respins are highly expensive. So we need to make sure that we verify every transformation in the design flow. There could be various transformations. We convert spec into behavioral model. Then the functional model will be converted into synthesizable model, RTL. Then the RTL will be converted into netlist that happens through synthesis. Then we insert the test logic that happens through DFT. You see, there could be various transformations. And similarly, there could be various transformations happening in the PD flow, physical design. When it comes to ASIC, we make sure that we verify every transformation. So verification becomes very critical. Verification becomes very critical for the success of ASICs. That's where we use FPGAs extensively for ASIC prototyping. So what is ASIC prototype? You think about A17. It's very complex. So we can't verify it thoroughly using simulation. Obviously, the simulation is going to be very slow. That's where we try to run the simulation on the hardware. So there could be various options like we can use hardware accelerators. We may get these accelerators or emulators from EDA companies. Also, we can think of creating custom board. That's what we mean by ASIC prototyping, how we create the custom board. What it means is we create the PCB with multiple FPGAs and we take the chip A17, we partition the chip into multiple blocks because you can't implement the entire chip on one FPGA because FPGA's capacity is very limited. You can't have 19 billion transistors in one FPGA. That could be some FPGAs that can have multi-billion transistors, but whatever that's available commercially. Also, we need to take care of the expense. We can't simply go for advanced FPGAs for prototyping. Cost is important. So if you go with standard FPGAs, we can't think of implementing the entire chip on one FPGA. So we have to use multiple FPGAs. Obviously, it's going to have impact on the frequency, but we are not targeting the frequency. We are looking at only the functionality. So whatever we do in the simulation, we want to simulate real-time scenarios. Whatever we do in simulation, we want to generate real-time scenarios. That is possible with ASIC prototyping. How different things can happen on the smartphone. We would be able to simulate real-time scenarios and verify the chip thoroughly. That's where we prefer ASIC prototyping. So here the advantage is we get more performance because here the complete design will be on the hardware, FPGAs. We partitioned A17 into multiple blocks and we map each block onto each FPGA. Now the entire design is happening on the board, hardware, so we can expect more performance. If same thing has to happen in the software, and then on top of it, let's say you are going to try some scenarios, software scenarios, that's going to make the simulation dead slow. And that's going to take a lot of time. It's going to take months. So we try ASIC prototyping. Also, whatever we do on the hardware, it gives us more confidence, especially when we try real-time scenarios. That's called ASIC prototyping. We use FPGA extensively to verify ASICs. So there are two ways: application-specific integrated circuit and field programmable gate arrays for the implementation. All right. Thank you.